So one thing I never did, and I should, is tell you what the sources are for the material I've been talking about. And there are a couple of books and a couple of papers, and I'll list them, and so that's for future reference. So there is a book by Birkenhake and Lange called Complex Abelian Varieties. And there are two editions, and they are very different. So second edition contains much more information. I think for the material I covered, it's contained in either. That somehow was a basic background on complex abelian varieties and corresponding topics. There is also a book of Arbarella, Coronalba, Griffiths, and Harris, which is called Geometry of Algebraic Curves. This, in the first 20 pages, essentially, gives a very brief introduction to the Riemann's theta singularity theorem and has much more information about curves. There is a book by Gusa on theta functions, which gives you much more of the theory of theta functions and their modularity properties and anything like that, much more than I would cover. And then there are books by Mumford called Tata Lectures on Theta, one through three, which contains some more information about the geometry, I would say, of the theta functions and how they relate to Jacobians and so on. And this is sort of the, so this is the books. And for what I'm going to say about integrable systems, is there are three articles by Grushevsky, which I'm basically going to base much of what I'm going to say on, with some, shortcuts and so on. So Grushevsky, there are two articles in 1977 called in the Journal of Functional Analysis and Applications. It's called something like Solving PDEs using Algebraic Geometry. And there is a 1977 article in the Russian mass surveys. It's called something like Methods of Algebraic Geometry. This is roughly the title. In integrable systems. And these are the two articles where the main construction of the solutions of the KP equation was presented and discussed. I have to warn you, this is an English translation of the Russian article, and this was the time when the English translations were not particularly good. So take it with a grain of salt. There are typos in some crucial moments, and there are wrong words. And then there are articles in 2005-07, they're on the archive, characterizing Jacobians by flexes and trisecants. And I'll be happy to give you more precise information, but this pretty much determines the articles uniquely. There are also an article by Shiota in 1986 in Invenciones, which contains, there is one article by Shiota in 1986 in Invenciones. This contains a proof of so-called Novikov's conjecture, which I'll discuss in a moment. and it's included in the book here. So in volume 3, there is a copy of this article given, and it's rather readable. I won't cover it because I won't have a chance. So there will be some crucial things that I will unfortunately have to omit from the discussion. So I'll basically talk about this because it's a stronger result, and this means that some of the intuition that actually goes into the result will unfortunately be omitted. Okay, so these are the sources, and what I wanted to do today is I'll finish this discussion about theta constants briefly, and then we'll start actually looking at differential equations and why they appear in the theory of the theta function. Are there any questions on anything we discussed previously before we start in earnest? Okay. So recall that we have the theta constants are theta epsilon delta of tau. So this means at z equal to 0, and they are modular forms of weight 1/2 with respect to a group gamma 4/8. And so let me write down the definition of it for the record. So this is a set of matrices A, B, C, D in the symplectic group with integral coefficients such that A, B, C, D is congruent to 1, 0, 0, 1 mod 4, and the diagonal of A transpose B is congruent to the diagonal of C transpose D is congruent to 0 mod 8. Okay, so let me try to explain what this means. So this means, these are integers. So this is a G by G matrix of integers, and this is an identity G by G matrix of integers, and so on. So the condition is that this matrix is congruent to this one mod 4. So essentially it says all the entries of the matrix are divisible by 4 except the diagonal. Okay? And this condition, when you look at it, it's not even clear that what I wrote defines the group. It's even less clear that this defines the normal subgroup, but in fact gamma 4/8 inside SP2GZ is a normal finite index subgroup. And thus, if you take the quotient of the Ziegel upper half space by this group, gamma 4/8, is a finite Galois cover of the moduli space of principally polarized abelian varieties. Okay. This group will not be important for us, and this will not be important, but I feel trying to discuss the theory of theta functions without saying what the basic tools traditionally are is not a good idea. And the theorem due to Rauch, Igusa, Mumford in various instances, it's a bit more general, is the following: that if you consider the map from AG 4/8 to a projective space, map to a projective space, and let me admit what the actual dimension is. That takes a tau and sends it to the set of values of theta epsilon delta of tau, for epsilon delta being half integers, even is an embedding. So let me explain what even means here. So you see, as a function of z, theta epsilon delta tau z can be even or odd, depending on whether the scalar product of epsilon and delta, well, it's each of them is in 1/2, is congruent to 0 or 1 mod 2. Okay, and if it's for epsilon delta odd, of course it's an odd function, so its value is identical to 0. Its value at 0 is 0. Okay, and if you count the number of even ones, that's what you get. This is some linear algebra exercise. Okay. On the other hand, if you recall, we had another kind of theta functions. We had theta functions of the second order, this kind, and you can also construct theta constants of them. And the proposition is these modular forms of weight 1/2 for a group gamma 2, 4. And you can probably guess what the definition of gamma 2, 4 is, so you replace the 4 and 8 by 2 and 4. Okay? And there is an almost theorem due to Salvati-Mani that says, well, we'll need to have a new name. The map from AG24 to P to the 2G minus 1, because there are 2 to the G of these guys, that sends tau to the set of the values of these things for all epsilon, is an embedding. So you notice there are many fewer of these things than of this. Why do I call this an almost theorem? Well, the theorem does appear in print. You can read it. The problem is there is a gap in the proof, and it has not been fixed. So technically what is known is that this map is at most finite to 1, is generically finite. You can have a very good bound for where it's possibly not injective but finite to 1. But it has, this statement has not been proven, but this is certainly believed to be true, and it certainly is true in low genus. Okay, so let's do a couple examples. Well, a couple will be quite a few. So genus equal to 1. So the dimension of A1 is 1. Okay, 2 to the G minus 1 is also 1. And 2 to the G minus 1 times 2 to the G plus 1 minus 1 is equal to 2. Okay, so this is the dimensions of these spaces. So this means that there are no algebraic relations between the theta constants of the second order. So this is theta 0 and theta 1/2. Okay, just because there are only 2 of them, we're mapping a one-dimensional space. It's an embedding. I mean, it's actually, the closure is all of P1. Okay, so the only relation among the theta constants with characteristics, so there is a tau here that I'm not writing, is the following. It's theta to the fourth 0, 0 is equal to theta to the fourth 0, 1/2 plus theta to the fourth 1/2 0. Okay. How do you prove this? This is implied by the bilinear relation. So if you remember, the bilinear relation will allow you to express the square of any one of these guys as a polynomial of degree 2 in this. And if you just write this out, this becomes a triviality. Okay? As a side remark, you can also try to look at the odd theta. So you see there is a theta 1/2, 1/2. This is the only odd one, so 1/2 times 1/2 times 4 gives you a 1. So this is an odd function of tau and z. So if you evaluate this at 0, this will be 0. But if you were to first take the derivative with respect to z and then evaluate at 0, this will no longer be 0. And that's something interesting, and this is in fact equal to minus pi theta 0, 0, theta 1/2 0, theta 0, 1/2. So this is an indication that somehow the odd theta functions also play some role in the theory. I won't go deeper into that. There is a big study here. Okay. So this is all you have in genus 1. So this is the entire ideal of relations among theta functions, theta constants. So for genus 2, the dimension of A2 is 3. 2 to the g minus 1 is also 3. And 2 to the g minus 1 times 2 to the g plus 1 minus 1 is 9. Hopefully. Yeah. Okay. So there are no algebraic relations among the 4 theta constants of second order, and all relations among theta follow from the bilinear relation. So you can write them all out. There are just many, and it's unwieldy to do so, but it's not a big problem to do that. So this in particular tells you that A2 to 4, the moduli of principally polarized abelian varieties of dimension 2 with a 2-4 level structure is essentially the same as P3. Right? That this map, is the image is open. It does dance. Okay. So the next case is genus equal to 3. So in this case, the dimension of the moduli space for abelian varieties is equal to 6, and 2 to the g minus 1 is equal to 7. And I won't even write out the third number, it's huge. It's 35, but never mind. Okay. So we introduce the following notation. So Sg of tau is going to be the following expression for any genus. It's going to be 2 to the g times the sum of theta epsilon delta to the 16th of tau minus the sum of theta to the 8th epsilon delta of tau quantity squared. Right? So this is a polynomial of degree 16 in theta constants. So this is a modular form, actually, for the entire group, with the entire symplectic group, of weight 8. Because you see, every theta constant has weight 1/2, so this is a polynomial of degree 16, so it's weight 8. Why it's a modular form for all of the symplectic group and not only for gamma 4/8? Well, you have to actually work out how the symplectic group acts on theta characteristics, on theta functions with characteristics, and it actually permutes them. And there are some 8th roots which disappear, so this works out well. Okay? So this is the claim, sort of. And the theorem that I'm not quite sure what the original attribution is, but certainly one place you can learn it is in a paper by Van Hemen and Van der Heer. Was the following, that S3 of tau is the defining equation for the image of A3 to 4 in P7 under the 2 theta, and there's a map by theta constants under the map okay. So what does this mean? Well, this formula, of course, I wrote down in terms of theta constants with characteristics. By using the bilinear relation, you can rewrite this as a polynomial also of degree 16 in these guys. And this polynomial of degree 16, the claim is the only algebraic relation among the theta constants of this type in genus 3. Okay? What happens for the theta constants of the other kind? Well, there is also a theorem due to Van Hemen, which says the following. The only algebraic relations among theta square epsilon delta in any genus are quadratic, and they are corollaries of the bilinear identity. So if you take this thing, this is a polynomial of degree 2 in theta constants of the second order, and these polynomials of degree 2 will satisfy a host of combinatorial like quadratic identities, sort of generalizing this one. And the statement is that all the algebraic relations you get among the squares of theta constants with characteristics are the corollaries of that. The conjecture is that the only other algebraic relations among theta epsilon delta. Notice the fact that the squares don't have any algebraic relations doesn't mean the things themselves don't have an algebraic relation. It could be an issue of signs, which somehow is very important here. Are quartic that are obtained from Riemann's quartic relation. This conjecture is also due to Van Hemen, and this somehow is I would argue, a major open question if you study the ideal of relations among theta constants. So what does this mean? So the Riemann's quartic relation, remember we discussed another example of the isogeny, so you take the isogeny from the fourth power of the abelian variety to itself, given by the matrix 1, 1, 1, 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1, minus 1, 1, minus 1, 1, minus 1. And as a result, you get a quartic identity for theta functions, which you can apply to get identities here. Okay? So that's what happens in genus 3. So again, in genus 3, though, I mean, the picture is complete in the sense you know the image under this map, and this is known to be true in genus 3 also. So in fact, in genus 3, there is essentially only one identity of this kind, which is equivalent to the one above. Okay, so the next case is perhaps genus 4. And I'll stop shortly, don't worry. I won't go to too high a genus. So genus 4, the dimension of mg is 9. The dimension of M4, sorry, is 9. The dimension of A4 is 10, and 2 to the g minus 1 is already 15. Okay? So trying to describe the entire ideal of relations among theta constants of the second order, in this case, is very hard, and the answer is not known. So what is known is that there is a theorem due to Igusa, which I stated at the end of last time, was that S4, this S4, is the defining equation for M4 level 2,4 within A4 2,4. So this is a subvariety of a P15, right? I mean the image of this map, it's an embedding in this case. And this is a divisor in it, which is given by this one equation. Okay? So this is essentially all that is known. Genus 5. So I won't even write down the dimensions, they sort of diverge wildly. But I'll say that there was a conjecture, actually from physics, that was due to Belavin, Knizhnik, Morozov, and Horker, Fong, there may be more people, which is the following conjecture, that S5, that SG in fact, vanishes identically on MG. So you see you have this modular form of weight 16 in any genus, and for genus up to 4 it certainly vanishes identically on MG. For genus up to 3 it vanishes identically. I didn't mention the fact that it vanishes in genus 2 and 1, but if you rewrite it using Riemann's bilinear relations in genus 2 and 1, it just becomes identically 0 as a polynomial in these guys. So that's true. So why did they conjecture something like that, and what would physicists have to do with it? Well, you see this thing, so the sum of theta to the 16 for the physicists, epsilon delta, this is for them a theta function corresponding to a lattice d plus 16, and the sum of theta to the 8th for the physicists, and I mean this is a correct statement, is the theta function corresponding to a lattice E8. And I won't tell you what a theta function corresponding to a lattice really is. And then the physicists say that the SO32 and E8 cross E8 theories are dual, whatever this means. This statement you may have heard or seen on the blackboard and some physics talk. And somehow this would imply that this theta function should be equal to this theta function for physicists. And that's why this conjecture was made. There is one problem with this conjecture. It would be very nice because this would give an explicit equation for the Schottky locus. The problem is the following, and that this we proved with Salvati-Mani, that this is false for any genus starting from exactly 5. And in fact, the 0 locus of S5 on M5 is the divisor of trigonal curves. So, I mean, if you don't really know much curve theory, this is just some very explicit divisor. So this is a curve that admit a 3-to-1 map to P1. Okay. And by the way, the reason it's called SG is this is sort of the Schottky form. So in genus 4, this was discovered by Schottky, though he did not write this expression for it. Okay. So this is pretty much all I wanted to say about the most classical version of the Schottky problem of trying to write down algebraic equations for theta constants. This is, to the best of my knowledge, all that is known in that direction. So if you wanted to write down all the equation for A424 in P15, it's not known how to do it. If you want to write down equations for M5 within A5, it's not known how to do it either. Okay. So this is finally the end of the introduction, and we're now going to go to integrable systems, unless there is some question or objection or suggestion.
So what are you proved was that conjecture was for
Yeah.
any g
For any g equal to 5. But you see somehow,
equal to 5 or greater than
for any g greater than or equal to 5. So you see somehow if it fails for genus 5, it should fail in higher genus also, because you would take a union of a curve of genus 5 and a fixed curve of other genus. And this thing will somehow factorize in such a way that it will fail. So, I mean, you essentially only need to do it for genus 5. Okay?
So this theorem has that there are theories, critical theories,
So the story is as follows. This conjecture was made in, it was made first in 1986, I think, and it was made last in 2002, okay, by various groups of physicists looking at this. And we proved this, I guess, last year, right? And after we proved this, there was a paper by two physicists. I'm afraid I'll misspell their names. So I remember the name of one, but not the other. Who claims that, of course, the fact that SO32 and E8 cross 8 theories are dual should not be interpreted to predict this. It's a physics paper, and I don't feel I am qualified to comment on that. So it certainly appeared after the result that this conjecture is true. So what the correct physics prediction would be, I don't know. This prediction is certainly false. Whether there is a justifiable correct physics prediction remains to be seen. So the only paper since was that this prediction is false and there should be a correction. What the correction is remains unknown. The reason we started doing this was not because of this conjecture. We were actually computing some superstring scattering amplitudes, and this quantity naturally arises there. But that's a completely different story. Yeah, Fong is a mathematician and a physicist. So he has two different persona. One is the one that works on Ricci flow and energy and differential geometry, and the other persona writes physics papers. And this is Fong, the physicist. So it was a physics paper in which the conjecture was made.
The same guy.
The same guy, yes. But when you talk to him, he can switch from one mode to the other. So, I mean, Fong, the mathematician, would not probably take credit for the conjecture. Fong, the physicist, would. I mean, it's still very important. I mean, this conjecture stimulated some research in superstring theory, so it was very important. And, I mean, the corrections to it would presumably be also important, but that's not known. So anyway, this is sort of finally, in the middle of the 5th hour of the phase, this is the end of the introduction in a way. So by now, I think I've defined everything I wanted to define, and I've proven all the basic results. I'll be very happy to discuss them with you at length or privately or in more detail. Just ask me, I'm here. Okay, so now I wanted to start moving towards integrable systems and differentiation and so on. This will be a somewhat different style. So this, so far, I tried to make as geometric as I could. From now on, it will become gradually less geometric. So there'll be things which I won't have a good geometric interpretation for, and there'll be formulas on the blackboard, some of which will be long formulas. And this, for me, is not a long formula. Okay, there'll be longer formulas. And unfortunately, or fortunately, depending on how you look at it, the formulas will be crucial. So we'll have to do them, and we'll have to look at the computations. And in a few places in the proof of the trisecant conjecture that I'm hoping to present, there will be somehow a miraculous result of a computation. So you just sit down and compute for a page, and you get the right answer. And there is no a priori reason I know of, or Grushevsky knows of, why you should be getting the right answer. Okay? So I apologize in advance for doing some tedious computations on the blackboard. Okay? Whether I'll prove the full version of the trisecant conjecture or just some parts of it, we'll see depending on how we're doing on time. But anyway, let's start. Okay? Questions? Okay. So this is a new topic of how you get differential equations for theta. Okay. So let me remind you that for any abelian, for any principally polarized abelian variety A theta, we have the Kummer map, cum, A quotient by plus minus 1 embeds in P 2 to the G minus 1. Okay. And for a Jacobian, we have trisecants. And trisecants, let me remind you of what the formula was. So this was the Kummer image of P plus R minus S minus Q, wedge Kummer image of P plus S minus R minus Q, wedge Kummer image of P plus, the last one I didn't add, Q minus R minus S is 0. This was the formula for the trisecant, right, where P, Q, R, and S are 4 arbitrary points on the curve. Okay? So this is an algebraic equation of some sort for theta functions, right? For the second order theta functions at z, right? But this is a 4-dimensional family. So let's now deform it. So for the map of the curve to its Jacobian, we choose, say, P as a starting point. Which is to say that for any x on the curve, we map x to x minus p as a point in the Jacobian. The Jacobian here I'm thinking of as p knot. Okay? So this essentially means that p maps to 0, right? So now I want to degenerate the trisecant. By letting, say, R go to P along the curve. Okay? So what does this mean? It means R is going to be equal to P, and there are, by the way, there are going to be lots of Taylor expansions that I'll write down, and they're crucial to the study. So it will be P plus some U times epsilon, where for epsilon in C very small. Okay, but what I really mean is the following. So, I mean, this is somehow a wrong way to think about it. So let's think about it more carefully. So we have the curve sitting inside the Jacobian of C, right? And we have P that maps, and let's call this map maybe AJ for Abel Jacobi map. So P maps to 0, and R maps to R minus P. Of course, R minus P, I mean, if I think of R as point on the curve, I don't know what this means. So this means, I mean, I map this to some, so R maps to the Abel Jacobi image of R, which I'd like to think of as a point on C to the G locally. Right? So of course I'm mapping to the Jacobian, but the universal cover of the Jacobian is C to the G. So locally the picture is, here is your C to the G, and here is your curve. So the point P gets mapped here, and the point R is somewhere out here, right? So this is not P, this is the Abel Jacobi image of P, and this is the Abel Jacobi image of R, right? And this is all in C to the G, so we have a curve, okay? So if I want to understand what R is, so the Abel Jacobi image of R, so I mean there was something here that was somehow a bit sloppy. So when I'm writing this is a divisor of degree 0, right? I'm not actually adding points. I mean, this is a divisor. This is a divisor class which I can consider as a class on P knot. But now I want to sort of localize this, so I'll need to do this as a computation in the complex space. Okay? So this means that the Abel Jacobi image of R is going to be the same as, I mean, so it's this Abel Jacobi image of P plus U epsilon for epsilon in C to the G, for epsilon in C small, sorry. So I want to say this. And U is the tangent vector to the Abel-Jacobi image of C at 0. Right? So, I mean, again, here is the curve, and here is P, the Abel-Jacobi image of it. Here is R. And of course, if I want to approximate R, I do a linear approximation. So I write the tangent vector to the image of the curve C at a point P, and I move along that. So that's the first approximation, right? So that's my approximation. So let's plug this into here. Okay? So let's just do this, and of course this is only the first term, but this is supposed to vanish for any R on the curve. So in particular, the first term in the first non-trivial term in the Taylor expansion will vanish. So let's write this. So we get then the Kuma image. Well, P maps to 0. So R maps to U epsilon minus S minus Q. And notice when I'm writing this is really bad, right? Because this are points on the curve, and I'm subtracting them. So instead of writing this, let me be careful for once, and let me write the Abel-Jacobi image of S minus the Abel-Jacobi image of Q. Right? Of course, nobody working on the subject ever writes this, but that's what you really mean. So, I mean, I want to say P gets mapped to 0, R gets mapped to U epsilon in C to the G. These points get mapped to the Abel-Jacobi images, right? So that's what the first thing becomes. The next thing is the Kummer image of, let's see, P minus R, so this is minus U epsilon, plus the Abel-Jacobi image of S minus the Abel-Jacobi image of Q. That's the second thing. The third thing is, again, there is P minus R here, so that's minus U epsilon, and now it's plus the Abel-Jacobi image of Q minus the Abel-Jacobi image of S. And this is supposed to be 0. Okay? So now let's try to think about the expansion of this in Taylor series. So what's the lowest order term? So let's see. So you see the Kuma image the Kuma map is symmetric. The Kuma image of Z is equal to the Kuma image of minus Z, right? It's a map of A quotient by plus minus Y. This thing is the same as minus this thing, right? So what this tells you essentially that the Kuma image, and I'm sorry, I can of Q minus S, so I mean Abel-Jacobi image of Q minus S minus U epsilon, which is the Kummer image, and I'll write this Q minus S, so I change the sign here so it becomes plus U epsilon, which is the Kummer image of S plus Q minus U epsilon, I flip the signs here, is 0. Right? So let's look at the lowest order term. So if epsilon were 0, this is certainly true because this is just the same point. Okay? So if we expand this now, there will be something here which will vanish because it will still be. So what's the linear term in epsilon? If I get the linear term in epsilon from here, then it will vanish because there is no epsilon here. So the interesting linear term will be the following. So this means that the linear term of interest will be the Kuma image of Q minus S, which the derivative with respect to U of the Kuma image at Q minus S with respect to U, which the Kuma image of Q plus S has to be equal to 0. Right? This is the linear term of the expansion of this in Taylor series in epsilon. Right? So how does the linear term come out? It comes from one of the three things. The terms coming from here and here will actually be the same. So, I mean, this is the same point, and you're just perturbing it in two different directions. In the direction, in two different, I mean, in the plus and the minus with respect to U. So that's the term you'll get from here, and this will just simplify. Okay? So that's the expression you get. So what does this mean? It means that if you look now at the Kuma image in the projective space, there are going to be 2 points on it. And if you take the derivative of the Kuma image at a point with respect to some vector U, these 3 vectors are going to be linearly dependent. if you start thinking of this as actually being in the projective space, you might get slightly confused. It's probably easier to think of this as actually in c to the 2g. So mentally, let's just think of this as in c to the 2g. It's easier to do so. The coefficients don't matter anyway. Right, so that's what we get. Notice this is now a differential equation of a certain kind for two theta functions, right? For theta epsilon of tau z. Because, I mean, this fact you can write as vanishing of many 3×3 determinants, which will involve theta functions and their derivatives. Okay, so that's not all that I wanted to do. So let's degenerate further. So now we'll add another point. So what points do we have? S and Q. So let's let S approach P. Okay. So now, if we just let S approach P, we need to expand in Taylor series again. So what I want to write is that S, the Abel-Jacobi image of S, properly speaking, will be the Abel-Jacobi image of P plus U times some delta, right? That's how far we are. But if I just expand to this order, I'm not going to get anything particularly new. I mean, I'm just going to vanish identically. So I'll need the next order, and I'll have V delta squared, where V is the vector of second derivative. So let's see. So we have this curve in the c to the g, and it has a vector of second derivative. So V is the second derivative with respect to x of the Abel-Jacobi image of x at x equal to p, where x is a local coordinate on the curve near P, right? And there is no way to write it that's much better than this. Of course, if you think a little bit more about it, it's not so bad. So U was just the values of the abelian differentials at the point P. The V are the values of the derivatives of the abelian differentials at point P. So in fact, for a basis omega 1, omega g of abelian differentials on C, U is a set of values of the abelian differentials at the point P, and V is a set of their derivatives. Okay, where the derivative with respect to the local coordinate on the curve. And if you choose a different local coordinate, it's the same projective point, so it doesn't matter. Okay? So if we plug this in, we're going to get some mess, right? I mean, not such a big mess, but we're going to get here, there is going to be Q plus some perturbation. There is going to be Q plus perturbation, Q plus perturbation again. Okay? So as a result, by expanding on Taylor series, the lowest non-trivial term is going to be the following. Well, there is certainly going to be the Kuma image of Q in there. That's not so surprising. There is certainly going to be the U derivative of the Kuma image of Q in there. Just, if you evaluate this at s equal to 0, that's a Kuma image of Q. And you evaluate this at s equal to 0, you get the derivative at U of Kuma image of Q. But then, of course, the next term will presumably involve a higher order derivative. So if you expand just linear terms, it will vanish automatically. So the next term, in fact, will be the following. It will be d squared U plus dV of the Kuma image at Q is equal to 0. Okay. So this is the next degeneration. So we started out with 4 points. Over there, we let two of them collide. We now let three of them collide. And we just...
Are we using the same epsilon and delta?
So you have to be a little bit careful. There are two ways. I mean, you have to do a Taylor expansion that I was too lazy to do on the blackboard. So what you formally should do is there are two approaches. First, you just expand an epsilon. You get this equation. Then you forget epsilon completely. You write down S using delta only. And here you use Taylor series and delta. Okay, that's one way you can go. The other way you can go is you can have from the start Taylor expansion in both variables and write down the first non-zero term in this expansion. You'll get the same answer. Did I answer your question?
My question was if epsilon and delta are related to the function of two variables, the delta function of two variables.
No, so epsilon and delta are just small parameters in which I'm trying to expand. So what I'm trying to say is the following. So we have the curve. So we have a curve in the large dimensional space. There is a point P on it. I mean, so this is the image of the curve in C to the G, right? And we have two more points, S and R, right? And now I want all three of these points to come together. And I somehow want to expand this in Taylor series as the 3 points come together. So my coordinates are sort of going to be how far S and R are from the point P. So epsilon and delta measure how far they are, and U and V correspond to the geometry of this embedding of the curve in C to the G. So epsilon and delta are just arbitrary parameters. So this
large number?
So epsilon and delta should be small, right? Because if I'm doing a Taylor expansion. So this means I'm dropping the higher order terms. So I'm trying to expand locally. So for example, here I'm trying to say the following. So let's do this simpler, perhaps example. So we have the curve inside C to the G, and we have R tangent to P. So this means in the coordinate on the curve, R becomes very close to P. So R and P. So let me choose local coordinate on the curve near the point P, and let then epsilon be the local coordinate of R in this local coordinate around P. So when I say local coordinate, it means R is very close to P. It means epsilon is very small. Then I have to map this whole picture to C to the G. So I'm using, I don't know, the composite function rule for differentiation, essentially. That's where the U comes from.
So this is not the way that we can get the equation SG that you define?
No, this is completely unrelated. You don't see anything of this kind. So this is just a Taylor expansion with respect to two variables on a curve. And this curve is embedded in C to the G. So I mean, the whole picture is as follows. You have the curve, which is embedded in this Jacobian, and the Jacobian quotient plus minus 1 is embedded in P2 to the G minus 1, right? So this is AJ, this is the Kuma map. And what I have is I have the Kuma image of the AJ of P plus AJ of R minus AJ of S minus AJ of Q, okay? And on the curve, I have a point P, and then I'll have a local coordinate, which I sort of denote epsilon, near P on the curve C. And then I'm trying to compute the derivatives of the Kuma image with respect to this local coordinate, which I'm doing in two steps. I'm computing the derivatives here, and I call it a vector U, and then I compute the derivatives here. Okay.
So you just collect the terms for delta squared.
Yeah. So you collect the terms for delta squared. So to go from here to there, I mean, so you could just expand in 2 points at once. It just becomes a mess. So it's easier to do it one step at a time. So first I get this. I mean, this is true on the nose. I mean, it's not this is the first non-trivial term in the Taylor expansion. So it has to be 0 identically. So this is a formula that's true. So U is, U. So this is true for any Q and any S on the curve. Now in here, I want to set S to go close to P. And I expand this in Taylor series in this S. So this means I have to write it up to delta squared term. because if I were to write it just up to delta term, I wouldn't get anything interesting. This would just happen to be 0 because this thing will cancel this. I mean, these two things will certainly cancel this. Okay? So I have to write the next term. So I write the next term, which I never did because you can imagine that if I were to expand this up to second order, it will be slightly messy. So I'm claiming that the first order will vanish identically as the second order. And you can see there will be the second derivative here, the first derivative here, and so on. So if I just collect the delta squared term, I claim that this will be the delta squared term. So where this are u and v. This is just the coefficients of the expansion. Okay? Yes?
I have a question about the notation. What is omega prime? Omega 1 prime?
So this means, so you have a curve. On the curve you have a, choose a basis, maybe a nice basis adapted to cycles, I guess, of abelian differentials. They have values at a point, right? The value, I mean, they are sections of a line bundle, so their values are not defined so well. So I mean, this is not a point in c to the g, this is rather a point in pg minus 1. They're only defined up to a common factor. Then oops, if you choose a local coordinate at the curve near the point p, this is locally a function. You can, I mean, the differential omega is, you know, locally some f of z dz. Right? So omega prime is f of prime of z. Okay? So omega of, so when I write omega of p, I just want f of p. When I write omega prime of p, I want f prime of p. That's all I mean. And of course this depends on my choice of the coordinate z. But if I choose a different coordinate, all of these get scaled by the same number. So as a point in pg minus 1, this is well defined. Okay? And since my computation, to be completely honest, happens on the universal cover, because I mean I'm thinking of the map to c to the g now. I'm choosing a base point and so on. These are okay even in c to the g.
So I think it's well defined.
This is well defined as a point in pg minus 1.
Only
And this,
locally.
I mean, this is the values at my chosen point p, right? The point p was at one point.
If you change the local coordinate,
Then this will not change, right? Because if I were to write this as some function g of w, d of w, where w is another coordinate, you know, I'll have the common factor of dz dw that will enter all of these things, and I will have d squared z dw squared that will enter all of these things. So this is
in the notation you just differentiate g only, not w. So usually in that case you can get Hessian.
no, I mean, there is only one, I mean, the curve is one-dimensional. There is only one derivative. Two are two different coordinates, two local coordinates near P, right? So then if I write omega I of, in terms of z1, this is going to be some function f I of z1 dz1. If I wanted to write it in terms of, so z2, this will be f of z1 of z2, so that the transformation d z1 of z2. Right, so this will be f of z1 of z2 dz1 as a function of z2 times dz2. Right? So if I were to write now some other omega j, this will be, so this was fi maybe. So now I'll have fj of z1, z2 times the same Jacobian of the transformation, which is now one-dimensional. So this means that the omega I, so this means that fi of z1 over fj of z1 is the same as, you know, and this cancels. So this means this is well defined. If I now were to try to take derivatives, right, So this is a formal procedure. I just write derivatives here. Nothing changed.
But because it's in the P projective space, right?
Yes, and the projective space, this G tuple is well defined. If I choose everything, I mean, if I go to the Teichmüller space, I can get this well defined in C to the G. For this discussion, it's easier to go to the Teichmüller space anyway. Okay. I know we're over time, but if you permit me 3 or 4 more minutes, I'll finish something here. Is that okay? So let's put a star somewhere here, right? So star has to be true for any point Q on the curve, right? There is only one point left. U and V are now fixed, right? So now we can expand star in Taylor series in Q to all orders. Right? Not just to the second order, we can expand it to all orders. We could have done it from the start, but I wanted to do it step by step. So thus, we'll get an infinite sequence of partial differential equations. So this is partial differential equations satisfied by the Kuma map for Jacobians. Right? In each order you get a differential equation, maybe 0, I don't know. Okay? This infinite sequence is called a hierarchy, and in fact it's called the KP hierarchy. KP stands for Kadamtsev-Petveashvili, because it turns out this infinite sequence, this hierarchy, has appeared in mathematical physics before this. Okay? So we get this infinite sequence. So the first non-trivial equation is in fact the following one. So this means, now we expand in power series in Q. Right? And so if we expand in power series in Q and then evaluate at 0, notice the Kuma map is even. So the first order derivatives will vanish, right? So we might need to expand to a sufficiently high order to get something interesting. So the first non-trivial equation that we'll get from here is the following one. It's du to the force minus du dw plus 3/4 of dv squared plus c times the Kuma image of 0 is 0. Let me explain a little bit carefully the notations. What does this mean? This is the Kuma image. So what does this mean? It means you take the Kuma image. So this means you differentiate it. It's a Kuma image of z, and you evaluate at z equal to 0. So you take the fourth derivative with respect to some vector u. So u, v, w are vectors in c to the g. The first two of them I defined already. W is the vector of the second derivatives of these things. Okay? And c is just a constant. Okay? This is the first equation you get. And this is called the KP equation. So now let me just give you a little bit of philosophy of why what we're going to further do follows, and we'll stop. So you see, there is a theorem, remember, due to Gunning, that if there exists a one-dimensional family of trisecants, then we have a Jacobian. Right? This was the theorem. The way we got this equation was by degenerating trisecants. So what we expect, so the expectations in the increasing order of difficulty will be the following. The first expectation is if there exists a one-dimensional family of Q satisfying star, then we expect the abelian variety to be a Jacobian, because this is somehow a degenerate version of this. Okay. The second expectation is that if all the PDEs of the KP hierarchy are satisfied, then this means that the equation star is true to any order in the Taylor expansion. So we expect that this would mean there exists a one-dimensional family of Q, and then it will be a Jacobian. Okay. This is not so hard. The next thing is we think that everything is algebraic. So algebraicity of the situation. If finitely many, some n of G equations are satisfied, which is equivalent to there exists an n-jet of a solution Q of star at 0, then all equations are satisfied. And then we expect this to be a Jacobian. Okay. Finally, there was a conjecture due to Novikov, which was proven by Shiota, for which I cannot give an easy motivation, which is the following. The KP equation is satisfied, so just one equation, so n is equal to 1, implies everything. Okay. So this is I mean, I realize there is a disconnect here. There is hopefully some motivation. And then the last thing, which was conjectured by Welters and proven by Grushevsky, which is the goal for this lecture, is that one trisecant implies there is a Jacobian. Okay, and the KP equation, this is sort of a one jet of a family of flex lines. And this is sort of a zero jet, just one flex line. So again, remember, a trisecant was when you had this, then the degeneration of a trisecant is this, and the further degeneration is a flex line that is tangent to higher order. And this is a condition for having a flex line. The KP condition is a condition for having a one jet, a one parameter, one local Taylor, one Taylor expansion term of the deformation of flex lines. And the conjecture is that if you just have one flex line, you have a Jacobian. So most likely the version of the trisecond conjecture I'll prove will be that if you have one flex line, then your abelian variety is a Jacobian, which is just proving that if you have this one point Q, then you have a Jacobian. Okay? Proving the full trisecond conjecture will be similar, but require us to deal with difference equations instead of differential. I apologize I went over time, but this is the outline of what we're going to do. So in 2 hours we'll start by trying to understand why there are any differential equations in the picture to start with. Questions?